what else? Another FA cosine. Everybody sees that? FA here, this is 60, so cosine. And minus, correct? Because it's opposite all of them. But with this equation only, we cannot solve the problem. The two are unknowns, FA and FB.
Do you have to find forces for both?
Yeah, the question of the problem is what is FA and what is FB?
Oh, but in the first picture, we don't need that?
No, this was just I was saying. Usually we do like that,
Oh, okay.
but the architect decided to do that.
So you have
The designer. Okay, so let's see, put in the y direct.
FA sine 60 minus mg.
FA sine 60, very good, positive, and then minus mg. Equal to 0. Always equal to 0 because it's with static equilibrium. How did she hit?
Her bottle hit the table.
Ah, I was expecting.
That was her. I was like, wow, she's walking pretty well.
Okay, so now from here we can find FA, correct?
Yeah.
So from here we can find FA. Once I have FA, I can find FA. So let's have a look at the numbers. I give you some time to try to confirm that these numbers are correct. And then I'll have a question for you. FA is 2260 newtons and FB 1130. Anyone got it? Yes? So my question for you is, this FA, is it larger, equal, smaller than mg?
It's larger.
It's larger. So you see, if you go to the store, you are planning to hang this chandelier that is 200 kilograms. If you go to the store and say, oh, I'm going to get the cord that can hold 200 kilograms, well, it wouldn't be enough here. So you would have to get a better rope than just the one that can hold 200 kilograms. Did you understand? The mass of this object here is 200 kilograms. But this FA is bigger than 200 kilograms multiplied by G. And why? Because the only component that is helping us is the sine of 60, not the whole FA. The other component, the FA cosine, is compensating the FB. Okay, but this is just back to chapter 4, right? Now comes something more connected to torque. Can I erase?
Yeah. How did you get?
Yeah.
Is it exactly?
No, it's not exact because these numbers are large, so we are rounding them.
I got -5.
Oh, that is too far. Here?
Yeah.
So m is 200 multiplied by 9.8, so it will give you out something close to 20,000, no, 2,000, divided by a small number.
Are you in radians or degrees? I need to be in radians?
No, it's all degrees.
Right. I'm in degrees.
So, put in your calculator.
Yeah.
200 multiplied by 9.8. This is almost 2,000.
Yeah.
And divide that. Well, what do you get for the sine of 60 degrees? Tell me what is the number that you get for sine of 60 degrees.
0.866.
Okay, so if you divide 2,000 by 0.8, you cannot get 5. Yeah?
Why are we dividing by sine of 60?
I'm trying to find an 8.
But when I did FA sine of 60 minus mg, I got -4.7.
But do you know the value of FA?
Yeah.
How?
did it backwards. So once you get the value of FA, I plugged it back into here. I can get 0.
Then it could be because you already rounded the FA. But if you put exactly the answer that your calculator gives for the exact value here, the exact FA that you get, then it should be 0. Because that's how we get FA. We get it from 0. Okay? Alright, so now comes
Wait, can I take a picture?
Yeah.
For the people who just came in, can you just explain in general what static?
We are studying static equilibrium. And what do we need for static equilibrium? The sum of all the forces will be 0. The sum of all the torques is 0. That means there will be no motion whatsoever. I'm not going to be translating anything. I'm not going to be rotating anything. Static. Okay, so we just solved the problem with the chandelier is not falling, it's static there. Okay, so now I'm going to make a connection with torque. So far we didn't use torque. So there is a guy, he finds a huge rock on his way. Okay, so this is the rock on his way. And he's trying to remove the rock, but he's not strong enough. So he's smart, he knows about level arm, he knows about tools. He said, I'm going to get a stick. Put it here. So instead of trying to roll it, I bring this stick, and now I'm going to exert a force here. So he brings this stick, puts a little rock somewhere here to work as a support. And here he comes, and now let me put this one, that drawing is much better than mine, right? So he's trying to push it down. This is the force of the man to try to get rid of the rock. Okay? How is he going to get rid? Well, he's trying to do torque here, right? He's trying to rotate this stick so that the rock gets out of his way. And now the question is,
Another rock. You have to put that other rock underneath.
to get to serve as a support for this stick. Okay, so what he wants, so this is his stick. What he wants is, he wants the stick to rotate like that. That's what he's trying to do. Okay? And here, where the support is the x of rotation. What is torque? Torque, the torque for the man, is the force that he's exerting multiplied by the level arm. And so the level arm is related to this distance here. Everybody remembers this, correct? So, if he exerts a force, he got this stick, he exerts this force and still not enough. What should he do to try to increase his torque?
Change the axis of rotation.
Okay, very good.
Make the radius longer.
Make the level arm longer, so I'm going to write this one first. So, the larger, the longer the lever arm of the man, the better for him, right? Meaning better, meaning the torque that he exerts will be bigger. So instead of this small stick, he can get a bigger one and try to rotate. This is one way that is very good. But what is preventing him from rotating the rock? What is making his life difficult? The mass, the weight of the rock. The rock is on this side, saying, no, I don't want to be rotated. So there is this weight of the rock. So the weight of the rock is also doing torque. The torque of the rock is this weight and the level arm of the rock. Okay, so this little distance here, the connection with that will give the torque from the rock. So it's the weight of the rock, the force done by the rock, multiplied by its level arm. So one way for the guy to make his life easier, get the rock out of the way, is by increasing his level arm. Is there any other way that could also be helpful?
Can we, if we decrease the level arm of the rock?
Very good. So the other way is decrease the level arm of the rock.
But I don't know how he'd be able to.
How he picks this support, this rock, and push it closer. That's it. Okay? Do both things together, even better. Okay? So this is just for us to remember again this idea of torque and level arm. And that's the concept. Yes, Victoria? Yeah.
I don't really understand how the rock has a torque.
Any force that we apply on this stick will try to rotate the stick. So the man, so let me put the stick again. So he is the stick and he is the support. The man is trying to rotate it like this, right? And if there was just a man and there was no rock here, it would rotate easily.
Oh, is it like action and reaction? Kind of?
No, it's the weight of the rock here. The weight of the rock is trying to, I don't want to be rotated. I just want to come back down. Okay, so let's see, he moves it a little bit, but the rock brings it back. He tries and the rock brings it back. Okay. Okay, so the next problem now. Let me just summarize the story and then we'll try to solve it. I'm good that I have. So the first three items there we already know. Is the part for the force. Whenever I have to solve these problems, I'm going to let's wait for the noise to go over. We really need soundproof for this. Alright, so let's go. First thing that we have to do, draw all the forces on the drawing. That's what I did there. I tried to put all the forces. Choose a reference frame. Once I have all the forces, the reference frame, write the equations. What is the equation? This. Sum of all the forces in the x direction is 0. Sum of the forces in the y direction is 0 because I want static equation. That's the 1, 2, and 3 you already know. You have done it before. 4 is the new one. 4 is the new one because it's for the torque. How am I going to write the sum of all the torques being 0? I have to choose one point, which will be my x of rotation. In this problem, I choose here as my x of rotation. And then I can write the torque always with respect to that x of rotation.
Can you repeat that again?
Yeah? Say it again?
I just couldn't hear.
Yeah, it's tough. What we want, how we are going to solve all of these problems, sum of all the forces is 0. This part you already know, you already did in chapter 4. How you do that? You draw the forces, choose your reference frame, decompose things, and put sum of all the forces 0. Now how about the torque? How are you going to write the equations for torque? You have to choose one point in your object, which will be your x of rotation. Here I chose this point, okay, which was a bit intuitive point. But where you're going to choose is completely arbitrary. Keep in your mind that you're not going to rotate. So you put the x of rotation wherever you want. And then you will write the torque with respect to that point that you chose. Now, how are you going to choose this point? Don't try to think, oh, it would rotate in this direction, so this must be the x of rotation. There is no x of rotation because it will not rotate. So you can put it anywhere that is convenient for you. And then you write the equation for the torque. This is just a hint, but we'll solve problems and this will become clear. And what you also have to remember when you write the equations for torque, if it's going clockwise is negative, it's going counterclockwise is positive. It's not going to go clock or counter. But if the force would be trying to go clock, you put minus. If it would be trying to go counter, will be plus.
Wait, but like you said that it's the axis of rotation where you put it as arbitrary, but isn't the whole point that you want to put it somewhere that's going to give you a net torque of 0?
anywhere I put will give me net torque 0 because I know that the system is not going to be moving.
Oh,
Okay, so I can put it anywhere. So let's start with one problem that is not too hard, and we'll make it more and more common. So this one is two children. They found a beam somewhere and a board and decided to use that as a seesaw. So this is the board. Right in the middle of this board, they found a support, so they put this board right on top, the middle of the board right on top of that support. And they start playing. So they want to find perfect equilibrium. The boy is here, and the drawing is telling us that his distance is 2.5 from that middle point. Okay. And the boy is a little heavier than the girl. He's 30 kilograms. Okay. So this is the middle point of the board. The girl is going to go somewhere on this side, and her mass, she's a little lighter, she's 25 kilograms.
She's tiny.
She's tiny,
They
yeah.
both
Exaggerated.
You both are. You must be like 4 or 5.
From your days playing the seesaw, what would you do when you were a child? If you were the little child and the big cousin was on the other side, how would you make sure you could raise your big cousin? What would you do? Get close to the center or far from
Far
the
from
center?
it.
Far. Everybody has that, right? That's what the girl will have to do. So I'm going to move the girl far
Trick question.
to be able to. So then she doesn't want to raise her cousin. She just wants them to be at perfect equilibrium. So the question now is, where are we going to put her? Okay. Yes. 3. Very good. She got it immediately. We'll find that for you.
Okay, it's 25, 2.5. Okay, got it.
Wait, what?
That's we will find. You see, what Lior did was, I want to get the torque, the net torque to be equal to 0. I know how I'm going to be mg 2.5 has to be equal to mg x. That's what she did, but let's go through. Very good. Okay. What is that I'm studying is the board. So it's true there are forces on this pivot point, there are forces on the children. I'm studying the board. So I'm going to put all the forces on the board. Alright, so what I have on the board? The weight of the child is here. It's the normal force, which is equal to the weight. So M-A-G. The weight of the girl. Wait. The girl we are calling B, right? So M, B, G. These are the two forces on the board. What else?
Isn't there FN?
Okay, there is where?
Coming off of.
Yes, there is contact here, so there is Fn. I'm going to put that
Isn't there
Fn.
also when we're sitting? FN?
There is where? The Fn where
Coming
this,
off
Where
their
they're
head.
sitting.
but on them. I just want to worry about the board. There is Fn on the boy, there is Fn on the girl, but I'm studying the board. Okay, so I'm just going to put the Fn from this support here. There is Fn. Is there any other force? Think carefully.
The weight of the board.
Very good. The weight of the board. Where are we going to put the weight of the board?
Where the trunk sits.
Right in the center of mass, and we chose to put this support right in the center of mass, so I'm going to put here the weight of the board. Very good. Okay, yes.
Why is it? Why is it that? Why don't we need to take into account the FN of
The boy and the girl, because we are not studying the boy. I'm just studying the forces on the board. The
Why
board,
did you decide to study the forces on
because the board is the one that is going to be rotated. Oh, it's not going to be rotated. It's the one that could rotate, but we want them to be at equilibrium.
Does it even affect our calculations at all?
No, because remember when we solve these problems, I pick each object. I pick the bucket and put all the forces in the bucket. I pick the
So why is it
Holy.
important to even talk about?
the normal force on the child exists. If I would study anything about the child, I would take that into account. I'm
Well,
not.
on the test you have to say the board has mg and fn.
You think about this
Oh
one.
yeah.
This one, only if I wanted to get, for example, the Fn. This is not the question of the problem. It's good if the question is saying, make the diagram of all the forces, then you would have to do that. Okay? If you just want to find the x, fine.
It's not
It's
really
all-
relevant, right?
It's not going to be important. You
Because
will,
they cancel out.
it's more than that.
More than that?
It's more than that. You had that.
Yeah, I don't understand why the board has that.
Because it's touching. It's if you put suppose you had a column and you put a beam on the column. So the beam exerts a force on the column reacts and exerts a force on the beam. So
It's in the middle because why?
it's in the middle because I put this pivot point right in the middle. I chose that. Okay, so now I'm going to solve this problem. I want to find x. So this x is related to torque anyway. Oh, if you don't think about it, you say, okay, I'm going to follow the rules here. There is no force in the x, so don't waste your time doing the forces in the x. If you want to go to the forces in the y, all right. If I choose this frame, I can write the equations in the y direction. So I have the weight of the boy, negative. I have Fn. I have the weight of the board, negative. I have the weight of the girl, negative. All this equal to 0. Does it help us to solve the question of this problem? No. Yes.
Why are you saying that there's no force in the x? If they're rotating, they're moving in the x direction too.
But there is no force pushing or pulling in the x direction. There is no component in the x direction. What you're thinking about, the rotation is torque. So torque, yes, we will have to write torque. But there is nothing in the translational in the x. Yeah?
You might as well include it though because they cancel each other out. Because
Which
Fn
one?
equals mg in this.
Yeah, if you want to find Fn, you would use this equation. But
Why can't you include it anyway? Whenever you.
fine, you can do, but it's not the question of the problem. The question of the problem is what is that x?
Oh, we're assuming then that they're just staying in place, they're not rotating at the moment.
No, they are not rotating.
That's why it's static.
It's that.
Oh,
Jessica, did you see here that it's not just that Fn is not just the weight of the board? It's more.
So we don't need that equation.
No, we don't, unless the problem would ask you what is Fn.
Wait, why isn't Fn and board?
No, that's what she had said before, but
It's minus all the masses
there
also.
are things on top of the board. No? So Fn is all the weights involved.
So then it wouldn't be good to include it if that's not the question.
I know.
That's the equation in the y direction. That's it.
Oh.
But it didn't help with the question. The question is x. And the x will only show up in the equation for torque. Now comes my question to you. What we said is the x of rotation I can put anywhere. Where are you going to put the x of rotation?
The middles.
But why are you putting the middle?
because it's
Support is
easiest.
there, that's where it's-
That okay. That's what I was expecting. That's what we always do in our mind. I said, okay, if this is the support, it will rotate around this point. So that's why I'm going to put the x of rotation here. It will not rotate, so I could put the x of rotation anywhere if I want to solve this problem. I can put it even here, because it's not going to rotate. Yeah.
So say we didn't know the mass of the girl, but we did know the mass of the board. So instead it would be better to put the axis of rotation underneath the girl.
That's the whole point. The best thing, it will be it will become more and more intuitive for you. But the best thing is put the axis of rotation wherever there are forces that you do not know. Because then, what is torque? Torque is the force multiplied by the lever arm. If the force is right at the axis of rotation, what is the lever arm?
0.
0. Okay, so that's a good advantage to choose a convenient axis of rotation.
Can you say that again?
Torque is force multiplied by lever arm. If the force is right at the axis of rotation, or if the force is right at the hinge on the door,
Can you say the force you're talking about? Normal force or the force of
in this drawing, any force that is on the axis of rotation.
Oh, you're saying like in that force.
No. Normal force, weight of the board, any force that is on this point. What is the distance from the force to this point? 0. Okay, so the lever arm is 0. So that is very convenient. I don't need to take Fn that I don't know into account. Okay? Now let's go. Let's write the equation for the torque. What we want is sum of all the torques to be 0 because there is no motion. So did you understand? What you said was good. Okay? That's what we do, but it's more than that. This choice was motivated by more than that. Okay, sum of all the torques will be 0. This is my axis of rotation. I don't take this force into account. I don't take this force into account. Okay, the boy. The weight of the boy is trying to rotate this beam clockwise or counterclockwise. You see the boy here? Trying to go clockwise or counter? Counter. So plus or minus?
Plus.
So I'm going to put the boy here, plus. And the weight of the boy, MAG. And what is the lever arm for the boy?
2.5.
All right. Here I am, axis of rotation. I neglect these forces because they are right at the axis of rotation. And here's the girl, trying to go clockwise or counter?
Clockwise.
Clockwise.
Negative.
So negative. And let me put this in another column. MBG and the X. The lever arm is the X that I do not know. All this equal to 0. And so, what is the X? So this, now you know what Lior did in her mind immediately.
What?
Can you also do this as a center of mass
If I
Why
could,
is that?
Can you use it as a center of mass
Because
like for example?
that would give you the center of mass,
Positive.
but not the.
Oh, she didn't coordinate the colors. Okay.
Oh.
It's a fair. I got you. Yeah, you know. And then she's going.
You couldn't because you don't have. If you knew where the center of mass was, then you could try to find that X. But I do not know where the center of mass is
But it must be in the middle now because it's not moving.
Some
because it's not moving. Yeah, probably it may work. Yeah, it may work. It may work.
Why is the girls negative?
Because she's trying to move it clockwise.
Okay.
If we set x as this way, then y is at negative 2.5.
So the equation is for torque.
Right.
So I'm not looking at x direction, I'm looking for torque. So this is the x of rotation. Torque here is counterclockwise, right? Torque here is clockwise. So there is no positive or negative x. What is positive or negative is the torque. Yeah? One more. This one has more things. Okay, so so now we have another beam. And so here it is. They give us the mass of this beam. Uniform. When they say uniform, it's for you to know that the weight will go right in the middle of that object. That right in the middle is the center of mass. See, so I have this 20-meter long beam. The mass is 1,500, so the weight is right here in the middle point.
Wait, does it tell you that the weight's in the middle, or you're deciding that?
No, I'm reading there. I said a uniform beam. So if it says uniform, means that the mass is equally distributed.
Okay.
So the center of mass is right in the middle. Okay, so right in the middle of the beam is the center of mass, and that's where I'm going to put its weight. So here I have mass of the beam, G.
Sorry, can we go back to the previous problem for 1 second?
Yeah.
The clockwise and counterclockwise, in which direction everyone's moving in?
Okay. So this is the center. Okay. Now this force is trying. It will not do, but it's trying to do this. Forget about all the other forces, and this force is trying to do this. So do you see that it's trying to move this beam counterclockwise?
Yes.
So this will be plus.
Okay.
The torque from the boy will be plus. Now let's look at the girl. It's not going to move, but what is the girl trying to do? According to this x of rotation, the girl is trying to move it clockwise. So it would be minus the torque of the girl.
So it's just where everyone's trying to go.
Yeah.
Okay.
And more than that today is where everybody is trying to go with respect to that axis of rotation.
Okay. So say we had put the axis of rotation as where the girl is, they would both be trying to go clockwise.
So if I put right at the girl, so I forget about the girl. This one is still trying to go counter. But then I would also have to take into account Fn. Fn is trying to go clock. The weight of the board is trying to go counter. See, so depending on the x of rotation, I have to look at different forces and see what each force is trying to do individually.
Yay.
Okay. So let's continue here with our beam. Oh, next slide. What else do we have? Right here at the edge, almost at the edge, I'm putting a big printer. Okay. So there is the weight of this printer, big of the printer. So this is the weight. Let's look at the distances here. The whole beam is 20 meters. So this is 10 meters because we said it's uniform. So right in the middle. Right, Victoria, right in the middle here. Then this one they said is 5 meters away from that edge. So this whole distance is what?
20.
No, from here, not the whole beam. It's 20 the whole beam, but from here to here, 15. Okay, so let me put this 15 also here. All right, and this beam is on top of 2 columns, 2 supports. So I have here the edge, 1 column. Since it's touching it, there is normal force, and let me put this normal force pointing up. Now it's the reaction on the board. There is another column here at the other edge.
FA or FN?
Well, they are calling it FA but it's normal force. Here there is another column. It's again normal force. They decided to call it FB just to distinguish these 2 normal forces.
So then why
Yes?
shouldn't our center of mass be, so there's no support underneath the center of mass?
There is no what? No, there is no support here. The
It's
support
just
they put at
center
the
of
end.
mass.
Yeah, it's just where the weight of the beam is. Okay, we want to solve. We want to find FA and FB. This is the question of the problem. There is nothing in the x direction, so x will not help us. How about in the y direction? Sum of all the forces in the y direction has to be 0. What do we have in the y direction? You help me, let's put a frame here. X, y, okay.
A
FA, okay, what else?
plus FB
Plus FB,
minus M G
alright,
minus M printer G.
very good. Can I solve this equation?
You have two unknowns.
I have two unknowns. The two things that I want to find show up in this equation, so I cannot find, cannot solve. I need another equation. In the x direction, it doesn't, we don't have anything, so where I'm going to go? Torque. Sum of all the torques will be equal to 0. And then comes the question, where are you going to put your x of rotation? Remember, you can put it anywhere, so try a convenient place.
So either under FA or under FB.
That's the best.
Can you explain why again? Even though we have
Because I do not know FA and FB.
right.
And I can put the x of rotation anywhere. If I put here, fine. I can write the torque, the equation for the torque. But then my equation will have FA and FB.
Oh, but if you put it under FA, FA is going to equal to 0.
Right. So if I put it right here, then the torque from FA will be just here. So that's a good choice. So this is my choice of x of rotation. All right. So if I chose that one, let's see. You have to help me now how to write this equation for torque.
It's FA.
Oh,
10. Well, the R is 10.
10, okay. What is the force? Torque is force and level arm.
Down,
Right.
so it's
Oh,
So we are starting from this force.
negative.
Okay, so this force is trying to go clockwise. Negative, very good there. So I'm going to put minus that force.
Why are you
What
starting
force
with
is
that?
trying to go clockwise?
Oh,
The force of the
Look, this is the x of rotation. This is trying to go like this.
Okay.
You see? Everybody sees that?
Yeah, but what force is that? The M.
The m of the weight of the beam. Okay, so look at it. The weight of the beam is trying to rotate it in this direction. It's not nothing is going to happen here, but it's just the direction of this force. Yes.
Mhm.
So here, just put the force. What is the level arm?
10.
10. So everybody understands that the level arm is just the distance because this force is already perpendicular. Right? If it was not perpendicular, I would have to get only that component.
And we don't write FA anywhere?
No, you can, but then you will write FA multiplied by 0.
so, oh, it's just that.
Why is it 15 and not 5?
Wait, I haven't. Okay, but
Totally just by that.
this is the distance from the edge is 5.
Yeah.
This is 15 because the whole beam is 20.
Oh, the whole
Sorry, do you set that equal to 0? Like, if that's why am I so confused? If that's torque.
This is just the torque of one force. I still have to put all the others.
Oh,
But
we're
if
not
you said
We are not done yet.
If
It's
you
just
set
that I'm
it
many
equal to
questions.
0,
Huh?
but if you set it equal to 0, then how can you?
But that's not the sum. That's one
No,
of it
I
for
still
now.
have to put
Like,
more
that's
things.
for F.
Oh, once you put a plus,
Wait.
we're good. Okay,
Oh,
fine.
oh, we were
Wait.
saying.
Laura,
So
what was
from
the
this
question?
line-
My question was, how can you
Is
Except for
tell
the
that it's
plus or minus,
perpendicular?
it's fine because we move it to the other side.
I see here. This is the beam and this is the force. It's perpendicular.
That's so weird.
Okay.
Let's go to another force that is also giving us a torque. How about the printer? The printer there is trying to rotate clockwise or counter?
Clockwise, so it's
Okay.
negative.
Negative again. So let me put here another minus. Let me put the minus in red. So another minus G is mass of the printer. G. And what is the lever arm? 15.
Do you do anything with FB or no? For the torque, there's no torque for FB, right? 'Cause
Wait,
it's
I still have to write that. I still
okay.
have.
As a return.
Then comes the last force that is away from my axis of rotation, which is the FB. What is FB trying?
Yeah, so it's positive.
Positive.
Positive. Okay, so then I have here plus FB, and what is the level arm for FB?
20.
20 is the whole
Oh, I ran out of space.
and this is equal to 0. So you see, this was a good choice because with just one equation I was able to find it. Yes.
And then we do the same thing for the other side.
Now, with that FB, just come here and get a thing. No? So you don't need, you could, but you don't need to do that.
So is that 10 or perpendicular 0? Next to the MBG.
FB multiplied by 20.
Do we have the masses of the printer?
Yeah.
Yes, the masses we have.
It's 15,000.
So then you just plug everything and you'll get those numbers. I'm going to skip this one. It's the same kind of problem. So no need to do. Just if you try to solve, you'll find that this FA gives us a negative value. If it gives us a negative value, what does it mean? Was my drawing correct? No. No, it just means that my FA is actually pointing down.
Wait, what?
What?
So I'll come back to this at the end. Let me move on.
Isn't FA supposed to be going counterclockwise?
Forget about this problem. We just solved that one.
Okay.
And I'll come back to this one at the end of the class. So I just want to continue. Okay, so forget about this problem for the moment. The one that we just solved is this one, and these are the two solutions. Okay, FA and FB. Now let me go to another one that is not more complicated, just has more force. The drawing helps us a lot. So now what we have is again this beam, but now it is attached to this wall. It has a hinge. It's a big heavy beam. If I would let it by itself, it would just fall. But then we put some cord to hold it, and we now can even put a sign, a big heavy sign.
Arlene's bookstore.
Hmm?
Arlene's bookstore.
Yeah.
You know this textbook was written a while ago.
So let's put all the forces involved on the beam, right? So we are studying the beam. We are going to put all the forces on the beam.
Is that the hinge that circle?
Yeah.
Oh,
it's the
sorry.
hinge. My drawing is not so good.
So don't you have an FN coming from the hinge?
Good, Laura. It's more complicated than that. We have contact, so there is Fn, but I don't know what is the force that. See, it's a complicated thing that is going on. So maybe this beam is trying to go like this, or I don't know. So it's more than just Fn. Whenever you have some rigid connection like this, what we say is, well, there is a certain force on this hinge, and there is the reaction from the hinge. I don't know what is the direction. That's why I'm putting it like this. There is a component that is normal, but there may be more.
Wouldn't that be a force that's different from the FN? The FN is just FN, perpendicular.
Fn is
And
always
then separately,
perpendicular.
we also have this unknown force.
Yeah. So I composed all of these forces and I put this total. I call this the reaction from the hinge. Okay. And so of course there'll be x and y component, and the drawing is helping us. So I'll put this the x and the y component. So one question of this problem is already this. What is these two components? Okay, so the component of the hinge in the x direction, the component of the hinge in the y direction. Fine. I have other forces in this problem. H is from hinge. This beam is attached to this wall through this hinge. The force there, this is not, it's a rigid connection. So I don't know the direction of this force. It's more than just touching.
So
It's more than just normal. It's a complicated thing. I just guessed the direction, I put it there.
so you're putting your nail in this way.
But what if it's trying to go the other direction?
Well, we'll find. If my drawing is incorrect, I would find a negative sign and say, no. So the direction should be like this. I'm following what they put in the drawing. So the drawing already helps us.
Will we always receive the drawing?
This can be very complicated. Okay, so this is the frame. But let's put the other forces. We haven't finished yet.
MG at the bookstore.
Of this sign?
Yeah.
Okay, so I'll
M.
put here the big M from the sign. Mg is the weight. There is also the weight of the.
FT.
Okay, so let's go for Ft. This is a rope, a cord, and that is very easy. Wherever there is a rope, I don't need to worry about directions. I know that the only way for this rope to be tense is that the tension force is along the rope.
Otherwise it would fall.
Otherwise, it would deform. So it's
Just flop.
yeah. They give us this angle. The angle is, if you read the problem, 30 degrees. Okay. What else? There is one more missing.
Sorry.
MG at the bottom.
The beam. Yeah. So and uniform beam again. 2.2 meters. Right in the middle, I put the weight. Right in the middle. So this is 1.1 meter. And this is another 1.1. All right. Sum of all the forces in the x is 0. I'm starting from that. And what are the forces that you find in the x direction?
FH.
FH. So I don't know the angle. You're correct. We'll put FH and this angle. They didn't write to me. So I'm just going to put FHX. Because they ask the problem. They say, I want to know just the components.
Oh, we don't
So?
care about it. Yeah.
I'll put it as a component. What else?
FT.
Okay. Plus or minus.
Minus.
And FT
FT cosine.
cosine of the u. And that's it. There is nothing else in the x. This is 0.
And
I
you're
can-
doing it minus because it's what you
Yeah, they are opposite.
You don't know FT, right? So you have two unknowns.
I have to cannot see. So I'll leave it like that, like this, and I'm going to go to another one. So I'm going to write all the forces in the y direction now. Let's see if it helps.
So FHY, I guess.
FHY and this is positive. What else?
Minus MG.
Okay.
Minus MG.
Anything else?
Minus.
Oh yeah, sorry. FT sine 30.
Plus FT sine of 30. So now I put all the forces in the y equal to 0. Again, I cannot solve. I have two unknowns, right?
Torque.
So here I have the two unknowns. Here I have two unknowns. So the question of the problem is what is the component of h in the x, in the y, and what is ft? So all of this I do not know. So no, cannot skip. We'll have to go to torque. All right. So I'll put the equation for torque. Sum of all the torques will have to be equal to 0. And again comes the question: Where are you going to put your X of rotation? What is a convenient one? Huh? Very convenient to put it here, so I don't need to worry about these components of the hinge. Okay, so here I have my beam. I don't need to worry about the forces from the hinge because it's right at the X that I chose. So let's pick the first one that going to the right shows up.
So
So
minus
negative. Very
minus
good.
mg
So
times
minus mg, and what is the level arm?
1.1
1 point. What else?
minus big M.
Minus the big one from the sign, mg, and
1.2.
2.2. And what else?
Plus
Plus
FTY.
Plus ft.
It has to be the
Sine.
right direction, right?
Very good. It has to be perpendicular to the beam
Sine 30.
in the y direction, sine of 30, and the level arm or the distance now.
2.2.
2.2. Let me talk a little bit about what we wrote here. This term here, how did I write? I wrote the torque of the component of the force that is perpendicular to the beam multiplied by the distance. That's one way to write torque. So the component that is perpendicular multiplied by the distance. Alright? We know all the masses. So from this equation, we find Ft. Once I have Ft, I can find Fhy, I can find Fhx. Let me just correct one thing in this slide. You see the answers in this slide. They gave us Fty. We don't want Fty, okay? We want Ft. So I think it's 700 something. Did you understand what I said? So the answer here is Fty, but that's not what we want. We want Ft. The question of the problem is, what is Ft? Here is just math. Huh? Just you putting things in the calculator. Yes.
Can you explain again how you did the F R for, and why did you choose the F to be perpendicular instead of the
The torque, the definition of the torque is, how do we write torque?
either F perpendicular R
Or
or
F
F,
and the level arm.
yeah.
So here, what I did is I picked the F, this F, but the one that was perpendicular. So I picked Ft sine. And what is the distance? This whole thing.
But why did you choose the force to be perpendicular, not the R?
You could do that also.
Because, but either way you would have to break down force.
It's just that if you want to pick the lever arm, you have to remember the definition. What are you going to do? I'm going to write this force, the line of this force, and this distance here. So getting this distance, this would be the lever arm. That is not so easy.
Yeah.
Let's go for the last one.
So you get Ft and then you just plug it in.
Yeah, once you get Ft, you plug it here to get Fhy and plug it there to get Hx. But remember, the answer is Ft, not the Fty that is showing up.
Right, so we can just completely disregard Fy.
The problem is not asking Fty, it's asking Ft.
And
So
Ft
it's
is 793.8.
700 something, yeah? You got that?
I got 793.8.
793?
Yeah.
And you?
I got a 772.
I think it's 794. That's what we solved it before. Okay, now the last one. What is the problem? We have a ladder, here it is, against the wall. this is the ladder against the wall. Okay? The ladder is touching this ground, cement, made of cement. And what we have is, well, if this ladder would fall, would move, friction would try to prevent that. So against this motion, I have friction, which they decided to call FCX. But this is friction, okay? Also, because the ladder is touching the ground, I have normal force. And the normal force they decided to call FCY. Just to combine FCX and FCY and say there is a total force caused by this cement.
Sorry, did you say FCY is FN?
So FCY is Fn and FCX is the friction. The composition of normal and friction gives this FC. Okay. The question of the problem is, what is this FC? Okay, so the problem wants to know what is FC. So that means they want to know this magnitude and they also want to know this whole angle. Force is a vector, so they want to know the magnitude and the angle. There is more to this story. Let's continue. They give us the mass of this ladder. It's a uniform ladder.
FC is not on a rope.
On the rope? It's not a rope, that is a ladder. So it's a rigid object.
And the FC is not along that line.
No, because it's this composition of friction and normal force. The sum does not have to be necessarily along the ladder. Okay? Yeah, so this is a ladder. Now there is the weight of this ladder. It's uniform, so I'm going to put this mg right in the middle of the ladder. That's the center of mass. So right here, I have mg, right in the middle. The ladder is 5 meters, so this is 2.5, right in the middle. Okay? So this whole thing here is 5 meters. And the last thing is this ladder is touching the wall. The height of where it's touching is 4 meters. I'm going to put it here. And since it's touching, there is normal force. So I'm going to put there the normal force, which they decided to call FW from wall, but it's normal force. And then you may say, well, don't you have to put also some friction? Don't you have some friction there? In principle, yes. But what they are saying is that this wall is frictionless. So maybe it's a wall, it's a glass wall, wet. So the friction is very small. We are neglecting the friction. Okay? Yeah.
If there was no friction on the floor, would FC then be the same as the ladder?
No. Only if it's tension. Tension, because this FC, if it was like this, and I had just touching, it would be like that.
Right. So when
Normal force is always perpendicular. It would be a completely unrealistic case, just as that one is.
even though it comes down at an angle.
Like here, there is an angle here. It's not realistic.
But if it was realistic, the ladder would actually slide down.
It's not going to slide down because it's equilibrium. But if it was realistic here, I would have to take into account friction also. But even though I'm not taking into account friction, nothing will move. Because we put it in the perfect angle, we have some friction helping here.
So we're not counting FW.
We are not adding friction there. I have just this normal force. Okay, so we want to know what is FC, the total FC. And so I need to know the magnitude and the angle. And I also want to know what is that force from the wall.
Which is the FN from the wall?
Which is the Fn, yeah. So I want to know what is the Fn from the wall. And what is the force from the cement. Okay, let's go. Sum of all the forces in the x direction is 0. So what do we have in the x direction?
FCX and FW.
Right. Let me choose a frame maybe like this. So FCX is positive, and the wall is negative, and this is 0.
Then they have to be equal to each other.
Yes. And I cannot solve like that because both are unknowns. Sum of all the forces in the y direction is 0. What do we have in the y?
FCY.
FCY
And negative mg.
Negative mg.
minus mg0. So this one is good. I can find FCY.
FCY equals MG.
Very good. And I think the number is given there. Approximately 118, right?
So how do you plug it back in once you have FCY?
Because we still need to do torque. We don't have that.
We can't because I don't know that angle. So
Or you just need
we
to
have
use
to
torque.
go for the torque. Sum of all the torques is equal to 0. Okay. Where do you want to put your x of rotation?
Down at the bottom right there.
I prefer that one also. You can put it anywhere, but this one kills both of those components.
FCY and FCX.
And now comes an issue here. So here's the ladder. MG is trying to go what? Clock or counter?
Clockwise.
Clock. Okay, so I'm going to put negative MG is not perpendicular. It's not perpendicular, so either you will have to find this angle here and put the MG perpendicular if you want to put this whole distance, or, and I'm going to put this, you will have to find what is the level arm for this force. I'll put it like that and we'll think a little later. Let me just complete the whole equation. Alright, what else do we have? Let's see, I have here, this is the ladder, I have here the wall, the force from the wall trying to go, clock or counter,
So
Counter.
plus,
is that one perpendicular?
No, it's also.
again that's issue. That one is not perpendicular, you can see from the drawing.
Can
So,
you repeat the FW one, please?
FW,
The y is plus.
here is the ladder, okay? Now the force is here. You see that I'm trying to go in that way?
Mm-hmm.
It's not so easy sometimes to see.
It would be easier to see if we put the FW a little bit lower down, because then we see the FW. If we were to draw the arrow for the FW, like 2 inches down, then we can see that FW is pushing the board in this
Yeah.
direction, which will cause.
But actually, in terms of the lever arm for FW, since we know 5 and since we know 4, we can just find, right, we're only looking for the x and
Very good, but let's see the definition of lever arm. Very good. You're in the right track. Let me just finish this equation. So I have here FW. Again, it's not perpendicular. So either you will have to find this angle, pick the perpendicular, and then use this whole distance. Or you put this force and you'll have to use the lever arm. All this is equal to 0. The problem now is what are we going to put here? Yes, Laura?
Weren't there, why aren't we including FCX or FCY?
Because we put the x of rotation right here.
Oh,
So
right.
the lever arm is 0.
Is FW positive because it's clockwise or because it's in the direction of torque?
Don't think about directions, x or y direction. We are thinking about torque. So if we are trying to go like this, it's counter clockwise.
Because it's counterclockwise.
So the plus is coming from the torque.
But MG isn't rotating.
MG is trying.
It's going. Oh, okay.
This is like a possible solution. If you like for the MG, can't you do? You have like the big right triangle. Can't you find the x value? In it?
Yes. So I think let's start from this. Here we have a big triangle. So we have a big triangle where this is 5 meters, this is 4 meters, this is right triangle. So this
That's
is
just
3, 4, 5.
3. Yeah. So if you don't know that, you just use Pythagoras.
3, 4, 5 triangle.
Okay. So this distance here is 3.
I don't remember.
But this whole distance here is 3. What is the definition for level arm? Who remembers that funny, weird definition for level arm? Is what? I have to go along the force, right? So let me pick this force mg. I have to draw a line along this force, okay? Here is my line. And the level arm is the distance from the axis of rotation to that line, so the perpendicular distance to that line.
So you do 2.5 and then. Oh, wait, say that again?
How do we find level arm? I draw a line along the force, so this is my line. And then the level arm is the distance from the axis of rotation to that line, so the perpendicular distance. So do you see that the distance is this?
Yeah.
This is the little r that I'm showing here. This is the level arm. So what is this value here? I already know that this whole thing is 3. What should this one be? 1.5. Very good.
How do you know that it's halfway?
This force is right in the middle of the ladder because it's the weight of the ladder. The ladder is uniform, so the center of mass is right in the middle. So here also will be right in the middle.
How do you know it's perpendicular? Yeah, that's the same question.
That's the definition of level arm. So definition is level arm is draw the line. Now go from the axis of rotation to that line, but perpendicularly
Perpendicular to what?
to that line,
Why to that line?
because that's the line of the force. That's the definition of level arm.
How do you know that the force is that line?
This is the force, the
Oh,
weight,
right. Okay.
and then I drew this line. So before I draw, let me see if anyone can get what is the level arm for FW.
The other triangle.
Very good. 4. Let's do that. So this is now the line for the F force on the wall. And what do I want? The distance from this axis of rotation all the way to that, the perpendicular distance. So this is 4. And so this is what I put 4 here.
Then you can find the FW.
Now we can find the FWs. Once I find this force from the wall, we can go back and find the FCX. Is that all?
No, you have theta.
Right. We want to find the hypotenuse, so we want to find the magnitude of FC and theta. Okay, so the answer of the problem are these things here. Not just the component X and the component Y, they want FC. So FC comes with magnitude and angle.
So you just
Use
the square
Pythagoras
root
and the
of-
tangent. That's
So
Wait, say that again. How do you solve it?
so you will find now. You will have a number for
theta's y
FCX
x, right?
and you will have a number for FCY. Is this the answer of the problem? No. How do we find FC?
FCX squared plus FCY squared square rooted.
So FC will be the square root of FCX
You're saying
squared.
if you have the triangle.
Right. So I use Pythagoras to get FC, and I use the tangent of the angle to get it. Yeah. That's it. That's the end of chapter 9.
So it's inverse tangent of y over x, right?
This is the end of chapter 9. I'll just come back to you on Monday to discuss that thing that I said, oh, if I get a positive or negative 4.
This is
Let me,
Meaning
Super
it's
easy.
all
It's fine.
First you find that you know that FTY is FT, so when you plug in you get FW.
It's like actually scary.
And get FTY, which you then use to get
What? It's like actually scary.
Yeah. Here we already have FCY.
Was it
With this,
like
I find FCX.
we had like our first test or second test? Like all separately.
Everybody will have the test on Wednesday.
Oh, thank God.
Okay?
Wait, during which period? We're in which slot?
In your period.
So everyone's having.
In your period. Everybody B and C will be on Wednesday. Can I just tell you, there is the next slide you can solve. Okay, this is an easy problem. After
Yeah.
that,
That's an abstract question.
after that, ignore.
Great. Oh, after that. Oh.
This problem of the muscles you can solve. After that, just ignore.
For sure. Okay, for sure.
There was a question for
I asked.
Joy.
So wait, so for the rest of chapter 9, we just, you just said,
Yeah, all of this. Then we start 10.